So, very good evening to everyone, and welcome to the NPTEL 7th live interactive session on mechanical behavior of materials, part 1. The course instructor for this course are Dr. Shashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shubham Jaiswal, I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. Okay. So sorry for the inconvenience. So in this live interactive session, we will be going to discuss some concept-related question, which will help you to solve your weekly assignment. So before proceeding further, in today's session, we will try to recapitulate what are all the things we have studied in week 7, and followed by some concept-related questions. And if the time permits, we'll try to solve some assignment question as well. So let's move further. So coming to the recap of week 7. So the week 7, we begin with the concept of cross slip of dislocation. So what is cross slip of dislocation? So it is a mechanism by which the screw dislocation moves out of the plane. Okay. So let me write. So this is a mechanism by which screw dislocations moves out of the plane. So let's consider this is our plane 1. Okay, so and this is plane 2, and this is, let's say, this is plane 1, this is plane 2, and this is again plane 1, as it is parallel to 1. Okay, so here we have a screw dislocation. Okay, so as this dislocation moves, it will cross slip and will go to this plane, and again it will cross slip and go to this plane. Okay, so this is nothing but a double cross slip. And in case of the screw dislocation, the Burgess vector and line vector are parallel or anti-parallel to each other. So there is no unique plane defined by the cross product of Burgess vector and line vector. So it means there are theoretically infinite number of planes are available for screw dislocation to cross slip. But there are some constants that are defined by the slip system, so which will restrict the number of planes for the cross slip to occur for the screw dislocation. And in case of screw dislocation or cross slips, there is always more than one plane will be available for screw dislocation to cross slip. So in screw dislocation, the Burgess vector is parallel or anti-parallel to the line vector, that is U vector. So as we have already talked that no unique plane is defined by cross product of the Burgess vector and line vector. So available. Okay. So there are some constraints. Defined by slip system. Yes. Always more than one plane is available for screw dislocation. So these are the things we have seen in the cross slip of dislocation, or we can say the first screw dislocation. So it is the mechanism by which the screw dislocation moves out of the plane. So in this case, here we have to remember that the cross slip is only for the screw dislocation. It is not possible for the edge dislocation. So okay, or just let me correct it. Okay. So after this, we have seen the how the missed dislocations are moved out of the plane. So the missed dislocation are have both the edge and screw dislocations. Okay, and it has the character of both edge and screw dislocation. So in this case, how the cross slip takes place, that we have studied. So let me write. Okay. So let us consider this is one plane and this is second plane. Okay. And here we have the missed dislocation. Okay, so here it is curved and the direction of Burgess vector is this. Okay, so here you can see that at this point it has a screw dislocation, and here it has the character of edge dislocation. So when the Burgess when the dislocation moves in this direction, so it will come to something like near to this place. Okay, this place. Okay, but as soon as it intersect means it touches the intersection line, so here, so the screw component of the dislocation will try to cross slip. Okay, and as the dislocation movement further proceeds, so what will happen? So this dislocation will cross slip. So and finally it will cross slip to this plane. Okay. So this is the missed dislocation. So here in missed dislocation only the screw dislocation cross slips, and rest of the part, that is the component of edge dislocation, gets regenerated on the new plane, and the intersection line, that is this line, will be along the Burgess vector. So let me write down some important points. That it has both screw and edge dislocation, and here that is on the nuclear. And also the third important point, that is the intersection line will be along the Burgess vector. So this is my mixed dislocation. Okay. So this is for the screw dislocation, like how the screw dislocation moves out of the plane. So it moves by the mechanism known as cross slip. So now, how does the edge dislocation move out of the plane? So to understand how edge dislocation moves out of the plane, so we came across the concept known as climb motion of dislocation. So what is climb motion of dislocation? So climb, it is the process by which the edge dislocations move out of the plane. It is the process by which edge dislocations move out of the plane. Okay. So now let's consider here we have one edge dislocation. Okay. And let's say here I have a vacancy. So let's say this is our extra half plane. Okay. So here is the vacancy. So let me see. This is vacancy. So what will happen on the application of the so what will happen? So this vacancy will come at this place, and this atom will go to this place. So here, what is happening? The new plane of the motion will be this one. So previously this one it was there. Now it will be this one. So what does it mean? So it means the dislocation is climbing up. So here we can say climb up, and as this dislocation is climbing up, so the vacancy is there, it acts as the vacancy sink. That is, the dislocation acts as a vacancy sink. Vacancy sink. Okay. So as here in this case, the vacancy is moving in, and the edge dislocation is moving up. So here vacancy moves in, and the edge dislocation moves up. So this is the climber. Now if we talk about the climb down. So let me draw the schematic.
इसका फिर डेरिवेटिव लेंगे, इसका डेरिवेटिव लेंगे.
So let's say this is the vacancy. So let's say this is the vacancy and this atom will try to come to this place. Okay. So what is happening here? So here the atom is occupying the position of vacancy and the dislocation is moving towards downside. So this is nothing but a climb down. Okay. So here in this case the dislocation acts as a vacancy source. So acts as a vacancy source. And here in this case the vacancy is moving out. That is, it is moving out of the plane and it is going inside the matrix, and hence thus dislocation is moving down. Here this is the climb motion of dislocation. Okay. Then after that, we have seen that how this climb motion will help the dislocation to surpass any barriers. Okay. So let's say this is my plane. Okay. So let's say this is my plane, and here I have an edge dislocation, and here I have any barrier. So what it will do? So it will try to surpass this. It will try to surpass this barrier. Okay. So what will happen? The climb motion will surpass any barriers by moving it out. So any barrier. Okay. So as we are talking about the vacancy in the climb process, so generally the vacancy diffusion is a temperature dependent. So this mechanism is only active on at higher temperature, and the activation energy of a diffusion is nothing but a vacancy diffusion barrier. So I mean what? Hence, it is temperature dependent. It means it is active only at higher temperature. Okay, so in this way we have studied like how the edge dislocation moves out of the plane. So if we categorize the motion of edge dislocation we can categorize in the two way. One is the conservative motion and second one is the non-conservative. Second one is the non-conservative. So, which is the conservative motion? The motion in which the number of sides are conserved, and in which case it's remain same, is nothing but a glide. Here, the non-conservative as is nothing but a climb motion, in which the number of sides are not conserved. Huh? No. Conserved. Okay. So this is about the how the screw and edge dislocations move out of the plane. So then after this, we have seen the concept known as kinks. So what is kinks? So it is the process of dislocation glide in which the dislocation moves in the steps. So process of dislocation glide in which the dislocation moves in steps. So let's say, so here, so this is my glide plane and here I have a dislocation. Let's say this is the edge dislocation. So here what will happen? So this is the direction of the Burgess vector. So as the dislocation moves, so what will it will try? It will try to form a steps. Okay, so it will move something like this. Okay. So here some steps are there, and these are nothing but kinks. Let's say this is my section L, this is my section M, and this is my section N. Okay. So as the dislocation moves, these kinks then move across. These kinks move laterally, and it will result in the average displacement of the dislocation. So here, if we see like the section L, M, and N. So here in L, the Burgess vector is perpendicular to line vector, and here in M, here you can see this is the direction of line vector, and it is parallel to the line vector, and here it has the Burgess vector perpendicular to line vector. So here it will be having the edge character, and it will be having the screw character, and it will have edge character. So in general, we can say that kink has a both edge and screw character. So so which result in a average displacement. have a displacement of this location. Okay. So here, as in this case, the dislocations are taking steps. It means there are some sharp corners are there, and these sharp corners will result in the increase in energy of dislocation. So these sharp corners will reduces the energy by minimizing its sharpness or providing some roundness. And the roundness of this dislocation will depend on the pulse Navarro energy value. So as you have seen that here one dislocation is there and it will try to bend or it will try to increase the roundness of the sharp corner. Pulse Navarro energy value. Okay, so this is about the kinks. Like it is the process of dislocation glide in which the dislocation moves in steps, and these steps are nothing but a clinks. So similarly, we came across the concept known as the jogs. So what is jogs? So in which the individual vacancy or the cluster of vacancies lead to climbing the steps. So the climbing operation will be done in the form of a steps rather than the whole row of atom shifting to new plane directly. It will move in form of steps. So these steps are nothing but a jogs. So let's say this is my plane, and here I have a dislocation which is climbing, and here some vacancies are there, or the cluster of vacancies. So what it will do? So it will try to climb up by forming a small skin. So let's say this is my section L, this is M, and this is N, and this is the direction of my Burgess vector B. Okay, so here in this case, at section L, the line vector is perpendicular to Burgess vector. Here at M also, the Burgess vector is perpendicular to line vector, and also at the section L, the similar case is there. That is, the Burgess vector is perpendicular to the line vector. So at L, Burgess vector is Here, Burgess vector is perpendicular to line vector. And at section EM, it is also here also Burgess vector is perpendicular to line vector. And at section EM, Burgess vector is perpendicular to line vector. So here, in case of the jobs, it is of the nature of edge character. Okay, so the jobs will be having the edge character, whereas kings, it has the both, that is edge and screw character. So these steps are nothing but the jobs. So both the positive and negative climb, that is the climbing up and climbing down, are processed by the nucleation of unit steps, and so this plane can climb up by number of jogs, like say, so let's say it will climb up like this. So in steps known as jogs. So these are nothing but the how the dislocation moves out of the plane. So for screw dislocation to move out of the plane, the mechanism is known as cross slip. And for the edge dislocation to move out of the plane, the mechanism is known as the climb. And when the dislocation glides takes in the form of steps, that that steps are nothing but a kings. And when the climb is taken place in the form of steps, this steps known as jogs. And the kings has the character of both edge and screw, whereas the jogs has the character of edge. So this is about the motion of dislocation. So after this, we came across the concept of resistance to a dislocation motion. Resistance to dislocation motion. So as the dislocations are generated inside a material, so there is some resistance will be offered by the core and lattice, and this will restrict the movement of the dislocation. So we'll see how it will restrict the motion of dislocation. So it will get a resistance from core of dislocation as well as lattice. So let's say I am having one material. Let's say, so here I have a edge dislocation. Okay, and these items are perfectly vertical. Okay, let's say, means there is no bending of the plane of the atoms. Okay. So in this case, the width of the dislocation will be this much. Okay, and now consider the case where these planes are bending due to the addition of extra half plane. So here in this case the width will be this much. Okay. So what is happening here? So the plane of atom is slightly bending around the this location. Okay, due to the means here it is showing some misfit. Okay. So now if we plot a plot of a energy by Burgers vector. So here in this case, let's see. Here, and if we take this is delta U by B, delta U by B, and if we take a 10% of it, let's say this is a this is a plus minus 10%. So in this case, this is the dislocation width. Okay. So what will happen? It will have a curve like this, which is tending towards the infinity. And here, if we see, this is the width of the core or the size of the core. Let me write. So in this case, okay. So here from this we can easily see that when the dislocation or the distortion or the size of the core is large, the dislocations are easy to move. When distortion of this location core is large, the dislocations are easy to move. Distortion of dislocation core is large, the dislocations are easy to move. Okay. So this is the resistance to the dislocation motion. Okay. So if the width of the dislocation is large, width, I am saying if the size of the core of a dislocation or the width of a dislocation core is large, then the dislocation are easy to move. Size of the core. Okay. So till this point, any doubts? Anyone? If any doubts are there, then please ask. So no doubts. Okay. So till now we are talking about the that is the width of the dislocation core. So what is the width of dislocation core? It is the distance over which the displacement of atoms are large enough that we cannot apply the linear elastic theory. Linear elastic theory. So this is nothing but the width of dislocation core. So diffusion over which the displacement of the atom are large enough that linear elastic theory cannot be applied. And it is usually of the order of B by K. Okay. So after this, we have seen the effect of W on the tau. So here, when dislocation coefficient is zero, that is no dislocation are present, perfect. So in this case, we will be getting the strength as that of the shear modulus. When dislocation width core size is of the order of Burgess vector, that is B, so this will reduce by the order of G by 400. Similarly, if we increase the dislocation width to 2B, so it will again decrease on the order of G by 10 to the power 40. So here you can see how the width of the dislocation core is affecting the stress required to move the stress required for the deformation. So this is about the resistance to dislocation by dislocation core. So here also we have seen one thing, that the dislocation glide, it occurs more easily in widely dislocation. So okay. So this is about the effect of the width of dislocation core on the resistance of it. So in general, the wider dislocations are found in metals with a simple close pack structure, and hence the materials are ductile. Hence the metals are generally ductile. While in case of the ceramics, they are tend to have a narrow dislocations width, and hence they have a high strength but are brittle in nature. And and also we have seen that the large interplanar spacing will lead to the wider core. Okay, so this is about the resistance offered by the core of a dislocation. Then we have seen the resistance to dislocation motion by lattice. So here, when we apply the shear stress to the dislocation phase will additionally experience a sinusoidal resistance due to the lattice. So okay, and this is given by the pulse Navarro energy, or the energy of pulse Navarro value. So here, and it is given by GB square pi upon 1 minus mu exponential minus 2 pi W by B. So, and the shear stress, that is the pulse Navarro stress, is given by 2G upon 1 minus mu exponential of minus 2 pi W by B, where W is nothing but the width of a dislocation core. And it is given by the equation W is equal to A upon 1 minus mu, where A is nothing but a interplanar spacing. Interplanar spacing. So, if we observe this equation carefully, and this is the energy, pulse Navarro energy. Okay. If we carefully observe this equation, that is this equation, okay. So you can see that if we need a shear stress to be minimum, pulse Navarro stress to be minimum, then the W should be large. It means the A should be large, and similarly the B, that is the Burgess vector, it should be small. Then only we will get a minimum stress. So here, as we have seen, that the A should be large, that is the glide plane with a wider interplanar spacing, and it implies that the densest plane. And when we talk about the B, it should be as small as possible. It means the slip along the direction with the shortest lattice translation, or also we can call it as the along the close pack direction. Okay. So this is about the resistance to dislocation motion through a lattice. Then after this, we have seen the slip systems. So we have seen the slip systems for different crystal structure, like crystal. Let me write down the slip plane and slip direction. So crystal is BCC, and the slip planes are 110 or 112 or 113, and the slip direction is A by 2 along 111. Whereas for FCC, the slip plane is 111 and the slip direction is along 110 direction. And for the SCP, we have the slip plane 0001, that is the vessel plane, and the slip direction is along A by 6 112 bar 0. Okay. So this is about the slip systems present in the different crystal structures. So similar to that, we have also seen how we calculated the planar density for the different planes in the FCC and BCC. So these are the things we have studied in the last week content. So now we will try to solve some problems based on the this concept, and some also as well as the some concept of last week. So here we have the first question, that is statement 1 to 3. So they have given one diagram and they have asked, in the above diagram, the post scenario of dislocation interaction as shown, where a step CD has formed in a parent dislocation line AB, which of the following statements are true or false regarding the dislocation? So the the first question is that the segment CD is a king. So please try to answer it, guys. It's very simple. Please try to answer it. Here you can see the given dislocation is of a edge nature. So now apply the concept of kings. Do you know the definition of kings? If you know, then easily you can answer. So what is king? It is the process of dislocation glide in which the dislocation moves in a steps, and these steps are nothing but known as a kings. So here, are you seeing any steps? No. Here there are no steps. So it means the segment CD is not king. So it will be false. Now the second question is, if the dislocation line ABCD has to move under the influence of tau A only, the motion of segment CD is non-conservative. So here we have a tau A in this direction. So now try to answer it. So it will try to move either in this or in this direction. So now you will try to answer it. So here you can see that the tau A is moving dislocation either in vertical or a downward direction. So the dislocation is moving through the mechanism known as glide, and the glide is a conservative in nature. So answer to this question will be false. Now try to answer for the third part. If the dislocation line ABCD has to move under the influence of tau B only, the motion of segment CD is only possible at higher temperature. So here, this is the shear stress tau B, and the dislocation line ABCD has to move under the influence of tau B. Then the CD has to move either in this plane or in this plane. Now try to answer. Any guesses? Okay. So, as under the application of tau B, the CD will change its plane. As it is the east dislocation, to move a east dislocation out of the plane, it follows the mechanism known as climb, and it is a temperature dependent mechanism. So, this statement is true. So this is the first question. Now here comes the second question. The question is like that. Consider the energy expended as a dislocation with a Burgess vector B and with a vacancy producing jogs moves through a crystal. Assume that the distance between jogs is d and the energy to produce vacancy is uv. Find the drag force per length FL caused by the jogs. Please try to answer it, guys. So first we need to know what is jobs. So what is jobs? It is an individual vacancy or cluster of vacancies lead to a climb in a steps rather than the whole row of atom. It will climb in the form of steps. So first draw the figure, then you will be easily answer this question. Okay. I will draw a diagram for you. Let's say this is my plane. Okay. Let's say this is my jog. Let's say this is my jog with the distance between jog is let's say this is distance d. This is my plane. Okay. Now try to answer it. And as this is the edge dislocation, this is the direction of Burgess vector. Now try to answer it. Where? What are the things they have given? The distance between the jogs is d and the Burgess vector b, and the energy to produce the vacancy is uv, and they are asking us to find the force per unit length. Now try to answer it. So here, when a dislocation of a length d moves a distance b. So in this case, the work done will be F into B. Okay. So here what they have given, the force is per unit length. So for the length D, the force will be FL into D. So work done will be FL into D into B. So this is the work done. Now if we apply the energy balance, that is the work done is equal to the energy required to produce a vacancy UV, then we can simply equate these two equations and we'll get our final answer. So this force per unit length will be UV divided by BD. So this will be our final answer. Okay. Now here we have the third question. So the question is like it. Consider the dislocation dissociation reaction. A by 2110 is dissociate into two Burgess vector A by 6, two dislocation A by 6 of 211 bar and A by 6 121 in an FCC crystal. And they are asking us to assume the energy per unit length of a dislocation is EL equal to GB square. And they are asking that the neglect any dependence of the energy on the age versus screw nature. So either it will be the age or screw, just assume the energy to be EL equal to GB square. And they are asking us to assume that this reaction occurs and the partial dislocation move very far apart. Neglect the energy associated with the stacking fault between the partial dislocations. And they are asking us to express the total decrease in energy per unit length of the original. So how much the total decrease in energy has been taken place after this dislocation is dissociated into two separate dislocation, A by 2 110, and that too in terms of A and G. And the second part of the question is like that: on which 111 must this dislocation lie? So on which 111 plane this dislocation should lie? So please try to answer it, guys. It's very simple. First, you need to find out whether the reaction is feasible or not. If feasible, then find out the energy before dissociation and after dissociation. Then do the for change in energy or the total decrease in energy. Then you need to subtract the energy after dissociation from the energy before dissociation. So in this way, you simply get the answer. Please try to answer it and tell me the answer. Any guesses? So what they have given that dislocation A by 2 110 dissociates into two dislocation. That is A by 6 121 plus A by 6 211 bar. Okay. Let's say this is B0, this is B1, and this is B2. The reaction is feasible when B0 square is greater than B1 square plus B2 square. Is it not? So let's find out the B0 square. So it will be A square by 4 of 1 square plus 1 square. So we'll get this is A square by 2. Okay. Now let's find out the B1 square. B1 square will be A square by 36, 1 square plus 2 square plus 1. And this will comes out to be A square by 6. Is it not? And here b2 will be a square by b2 square will be a square by 36 1 square plus 2 square plus 1 bar square, and this b2 square will also be a square by 36. And if we do the addition b1 square plus b2 square, it comes out to be, sorry, this is just 6, sorry for the mistake, it's a square by 6, so it will be a square by 6 plus a square by 6, so it comes out to be a square by 3. So since b naught square is greater than b1 square plus b2 square, the reaction is feasible. Okay, as this dislocation dissociation reaction is feasible, now we can calculate the energy. So now if we find out the energy initial, so it is given by g b naught square, because b naught square is the initial energy, and it comes out to be g a square by 2. And energy of final, here let me draw the schematic. This is b naught, let's say this is b1, this is b2. So this is energy initial equal to g b naught square, and here it will be E1 equal to GB1 square and E2 equal to GB2 square. So a final energy will be E1 plus E2. So this will be GB1 square plus GB2 square. So B1 square plus B2 square, and it will comes out to be G a square by 3. So the total decrease in energy is given by initial energy minus final. E initial is G a square by 2 minus G a square by 3. So if we solve, we will get answer as G square by 6. So this is the total decrease in energy per unit length of the original dislocation in terms of A and G. Now the second part is on which one plane must this dislocation lie. So let me add one slide. Here. Okay. So the B part is on which 111 plane, on which 111 plane must this dislocation lie. So on which 111 plane they are asking. So how will I answer this question? So there are 4 111 plane. One is 111. Second one is 1 bar 1 1, 1 1 bar 1, and 1 1 1 bar. So if this dislocation needs to be lie on the 111 plane, then 110 dot xyz should be 0, and the second, that is 211 bar into xyz equal to 0. Similarly, 121 dot xyz equal to 0. Now put this 4 plane in this in place of xyz and find out for which case it is coming 0. Try to answer it, guys. Any guesses? So if we do put this different 1 place in place of xyz, so for 1110 we will get 1 bar 1 1 and 1 1 bar 1, and here we'll get 1 1 bar 1, and here also we'll get 1 1 bar 1. So in all these three, only one plane is common, that is 1 1 bar 1. So thus dislocation lie on this plane. So this is our second question. Now coming to the next question. The next question is like that. A dislocation is anchored between 2 points 10 micrometer distance with points 10 micrometer distance for a metal with a Burgess vector of 0.35 nanometer and G equal to 30 GPa. Compute the shear stress necessary to bore the dislocation into a semicircle. Consider the alpha equal to 0.5. It's very simple. Please read the questions carefully and you will get the answer. Any guesses, guys? So first we'll write what are the things has been given in the problem. So they have given B equal to 0.35 nanometer or 0.35 into 10 to the power minus 9 meter. Similarly, G is given, that is 30 GPa or 30 into 10 to the power 9 Pascal. And alpha is given, that is 0.5. So the shear stress needed to bore dislocation is given by tau equal to alpha GB upon R. So we have the alpha, G and B. We don't know the value of R. So how to find out? So they have given that there are the 2 points. Okay. Let's say this is 2 points and they are at a distance of 10 micrometer. And the dislocation is moved, the dislocation is bored in the form of a semicircle. So if this is the radius, we have given the distance between 2 points, and that is nothing but a diameter. So we need a radius. So R will be equal to 10 micrometer by 2. It comes out to be 5 into 10 to the power minus 6 meter. R. Now put this value in this equation. Tau alpha is 0.5, G is 30 into 10 to the power 9 into 0.35 into 10 to the power minus 9 divided by 5 into 10 to the power minus 6. So if we calculate here, this will get cancelled out and this will come at 1.05 into 10 to the power 6 Pascal, or tau equal to 1.05 megapascal. Okay, this is the second question. It's very simple. The hint was given in the problem that both the dislocation into semicircle. So with this statement we find out the radius r. So mean the radius of curvature. So now coming to the next question. Consider the reaction of addition of two parallel dislocation of Burgers vector B1 and B2. What would be the Burgers vector of the product dislocation if they react with each other? Would the reaction will be energetically favorable? Please try answering this. So what they are asking, like this is dislocation B1. Let's say this is B2. They are forming the third dislocation B3. And they are asking whether this reaction is feasible or not. That is B1 plus B2 is giving B3. So B1 is given as A by 2, 110, and B2 is given as A 0, 1 bar 1. And they are asking what is B3 if B1 plus B2 equal to B3, and whether it is feasible. So for feasible condition, we need to check B1 square plus B2 square should be greater than B3 square. So first find out the B3 and then find out the square of all the Burgers vector, and then find out whether LHS is greater than RHS or not. So B3 is equal to B1 plus B2. So B1 is A by 2, 110 plus A 0, 1 bar 1. So this comes out to be A by 2 minus A by 2 and A bar. So if you take out A by 2 common, we will get 1 bar, 2 bar. And the B3 square will be A square by 4 into 1 square plus 1 bar square plus 2 bar square. So this comes out to be 4 plus 6, 6 by 4 means 3 by 2 A square. This is B3 square. Now B1 square is A square by 4, 1 square plus 1 square plus 0 square. So it comes out to be a square by 2. Is it not? And b2 square will be 2 a square. And b1 square plus b2 square is a by 2 square plus a square. Now, please find out. b1 square plus b2 square is how much? Let me cross check. 110, that is a square by 2 plus b2 is 2a square. So this is 2a square and it will come out to be 5a square by 2. Since b3 square is less than b1 square plus b2 square, it is physical. Okay, this was the third question. Now, coming to the next question. The question is like that: on which 1110 plane of BCC iron can a dislocation with a Burgess vector a by 2 111 move? So if a dislocation wants to move on 110 plane, then the product will be, their dot product should be 0. So 111 dot xyz equal to 0. And Burgess vector is a by 2 1 1 1. So we have 110 plane. So there are how many planes? That is 1 bar 0, 1 bar 1 0. Then we have 1 0 1 bar or 1 bar 0 1. Similarly, we have 0 1 1 bar or 0 1 bar 1. So these two planes are nothing but similar. That is 1 bar 0. These two are also same. That is 1 0 1 bar, and this is 0 1 1 bar. Now put all this plane in the place of XYZ and please find out on which 111 place BCC iron can a dislocation with a Burgess vector move. So if you put, so you'll get a 0 for all these planes. Is it not? So 1 1 1 dot 1 1 bar 0 equal to 0. 1 1 1 dot 1 0 1 bar equal to 0. And 1 1 1 equal to 0 1 1 bar equal to 0. So in these three places, the dislocation with a Burgess vector a by 2 1 1 1 can move. Sorry, guys. So now moving to our next question. Determine whether the dislocation dissociation reaction is feasible or not. Please try to answer it, guys. It's very straightforward. So if this dislocation or reaction is need to be feasible, then we should have it should satisfy the condition B1 square should be greater than B2 square plus B3 square. Is it not? So what is B1 square? B1 square is A square by 4, 0 plus 1 bar square plus 1 square. So B1 square comes out to be A square by 2. Is it not? Now we have B2 square. B2 square is how much? A square by 36, 1 square plus 2 square plus 1 square. So B2 square comes out to be A square by 6. B2 square. And if we calculate B3 square, B3 square will be A square by 36, 1 square plus 1 square plus 2 square. And this also comes out to be A square by 36. Now if we do B2 square plus B3 square, we'll get this should be 6. That is A square by 6. So A square by 6 plus A square by 6, which comes out to be 2A square by 6. It means A square by 3. So as x square by 2 is greater than A square by 3, the reaction is feasible. Okay. Now here comes the interesting question. Find out the ratio of elastic stored energy of an S dislocation to that of a screw. Assume energy of the core to be negligible. Consider Poisson's ratio nu equal to 0.33 or let's say 1 by 3. Now they are asking us to find out the ratio of elastic stored energy of edge dislocation to that of the screw. So what they are asking us the elastic energy of edge dislocation to the screw. Now please try to answer it, guys, as we have covered the energy of a dislocation for both the screw and edge. So use that equation and try to find out the ratio. So they are just asking us to find out the stored energy of a edge dislocation. Okay, so you just consider the elastic. They are asking us only the elastic stored, no need of considering the core energy. Let's try to answer it. Any guesses? Please try to answer it, guys. So here we know the elastic energy of a S dislocation is given by equation GB square upon 4 pi 1 minus nu into ln of R by R naught. And whereas elastic energy of a screw dislocation is given by GB square upon 4 pi into ln R upon R naught. So if we take a ratio, of screw, will get GB square upon 4 pi 1 minus nu into ln R upon R naught. Here also GB square upon 4 pi into ln R upon R naught. So this will get cancelled out and we only left with the 1 upon 1 minus nu. So if you put the value of nu, we'll get E elastic of edge to the E elastic of screw equal to 1 upon 1 minus 1 by 3. So it comes out to be E elastic E to the E elastic of screw equal to 3 by 2 or equal to 1.5. So elastic energy of S dislocation is 1.5 times than the elastic energy of a screw dislocation. So here comes the next question. It's a very interesting question. Just this one question is will consider all the concepts. So the question is like that: a dislocation in an FCC crystal with a Burgers vector B equal to A by 2 0 1 1 1 dissociates on the 1 1 bar plane into two partial dislocation of the A by 6 2 1 1 1 type. And so they are asking us to give the specific indices of the two A by 6 2 1 1 bar partial dislocation. And the second part is like that: onto what other plane of the 111 family could be the B A by 2 0 1 1 1 dislocation have dissociated. And the third part is give the specific indices of the two A by 6 2 1 1 1 type partials that would be formed if the A by 2 1 0 0 1 dislocation had dissociated on the plane in B. So what they have given B as A by 2 0 1 1, and what they are saying, and these are on the plane 1 bar 1, sorry, 1 bar 1, and they are saying that B2 and B3 are in the form of A by 6 2 1 1 1 type. So they are asking what is B2, what is B3. So please try to answer it. It's very interesting question. Please try to answer it. Please try to answer it, guys. Any guesses, guys? So let's solve this together. So we'll try to solve first part, that is A. So let the partial dislocation B1 equal to A by 6 x1 y1 z1 and B2 equal to A by 6 x2 y2 z2. Okay, now we know that this is B naught. B naught equal to B1 plus B2. That is A by 2 0 1 1 equal to A by 6 x1 y1 z1 plus A by 6 x2 y2 z2. Till this point it is clear. Okay, so now if we solve, what we'll get? x1 plus x2 equal to 0. Let's say this is our equation 1. Now here y1 plus y2 should be equal to a by 2. So here a by 6 is there, so it goes that side, so it becomes 3. So y1 plus y2 equal to 3. Similarly here we have z1 plus z2 equal to a by 2. Means a by 6 z1 plus a by 6 z2 equal to a by 2. So we'll get z1 plus z2 equal to also 3. So these three equations we got. Is it clear? Okay, till this point, if anyone has doubt, please ask. So what we did, we assume the two dislocation as B1 equal to A by 6 with some indices of x1, y1, z1 and B2 as A by 6, x2, y2 and z2. Now they are asking that this single dislocation is dissociating into two. It means this B naught is dissociating into B1 and B2. So B naught equal to be B1 plus B2. So we kept put the value of A by 2, B naught as A by 2 0 1 1 1, and we put the value of B1 and B2. So from this, it's just a summation. So we got the equation x1 plus x2 by x2 equal to 0, and y1 plus y2 equal to 3, and z1 plus z2 equal to 3. So here we have 6 unknown and 3 equation. So we cannot solve. So we need one more. We need some more equation to solve it. So what they are asking that this is dissociating on 1 bar 1 plane. So it means their dot product should be 0. Is it not? So if I say also partial lie on 1 bar 1, so we can write b1 dot 1 bar 1 equal to 0. It means x1 y1 z1 into 1 bar 1 equal to 0, which gives us x1 minus y1 plus z1 equal to 0. Let's say this is equation 4. And b2 dot 1 bar 1 equal to 0. That is x2 y2 z2 dot 1 bar 1 equal to 0. So here we have the equation x2 minus y2 plus z2 equal to 0. This is equation 5. So now we need to do the trial and error. So as they have given, this is the means the dislocation are the type of A by 6 2 1 1 1. So how many possibilities are there of 2 1 1 1? One is 2 1 1, 1 2 1, 1 1 2, 2 bar 1 1, 1 2 bar 1, 1 1 2 bar. Similarly, we have 2 bar and many more. Okay. So now put these possibilities in this equation 1, 2, 3, 4, and 5, and find out which of these two indices satisfy the conditions. That is x1 plus x2 equal to 0, y1 plus y2 equal to 3, z1 plus z2 equal to 3, and x1 minus y1 plus z1 equal to 0, and x2 minus y2 plus z2 equal to 0. So please try to put all these indices and tell me the answer. So, any answer, guys? So, if you put, you'll get only two indices. That is 1 2 1 and 1 bar 1, 2. So B1 will be A by 6, 1 to 1, and B2 will be A by 6, 1 bar 1, 2. So whether these indices are true or not, we can cross verify it by taking its energy equation, whether the reaction is feasible or not. So if you do, you will get that reaction is feasible. Okay. This is the answer of part A. Now here comes the part B. The part B, what they are saying, onto what other plane of 111 family could be A by 2 0 1 1 1 dislocation have dissociated. So B is equal to A by 2 and 0 1 1 1. And they are asking on what 1 1 1 family of plane they have dissociated. So here in this case, so what is the criteria? That B dot xyz equal to 0. So here we have 4 1 1 1 plane, 1 1 1, then 1 bar 1 1, 1 1 bar 1, and 1 1 1 bar. So put this value of 4 plane in place of xyz and try to calculate. So here we have a 0 1 1 dot 1 1 1 0 1 1 dot 1 bar 1 1, and here we have 0 1 1 into 1 1 bar 1 and 0 1 1 1 1 1 bar. So here out of this only this will satisfy the equation. So this will, that is 1 1 1 bar will be the answer. Okay. Now here comes the C part. So what they are asking, like in C part, give the specific indices of A by 6 211 partials that would be formed if the A by 2001 dislocation had dissociated on the plane in B. So in B, so this is also similar to the A part of the question. So I'll give you the hint and try to answer it. So here we'll have some equation something like this, that is x1 plus y1 minus z1 equal to 0 and x2 plus y2 minus z2 equal to 0. Please try to solve it and tell me the answer. Here they are asking, give the specific indices of two A by 6 to 2 partials that would be formed if the A by 200 dislocation had dissociated on the plane in B. So they are saying on this plane, that is B. So B is, which plane is there? 1 1 1 bar. At this plane they have dissociated. Okay. So all the equations like this will remain same. Only the change here in this equation, that is equation 4 and equation 5 will be there. So, so here only equation 1, 2, and 3 will remain same. Only the equation changes, that is 4 and 5. So the similar planes I have given 2 1 1 1 2 1 1 1 2 2 bar 1 1 1 2 bar 1 1 1 2 bar and many more. So please put this indices of the plane and tell me the answer. The final answer will come something like this. Okay, just try to solve 1 bar 2 1 and 1 1 2. So now moving towards the next question, that is on 8 cubes that have common vertex corresponding to the origin of the axis, draw the family of 1 1 1 planes and show that they form an octahedron. So I'll draw 8 cubes. Let's say I am just drawing 4 and it will the 4 will be the mirror of this. Like let's say this is my first 1 1 1 1 plane. Let's say this is my second 1 1 1 plane. Let's say this is my third 1 1 1 1 1 plane, and let's say this is my fourth 1 1 1 1 1 plane. So similarly on the bottom side also we will draw the 1 1 1 plane. So now try to answer it. It's very easy. Let me draw the rest of the 8. So let me draw for different 1 1 1 1 planes. And also I will have something and something like this. Okay, so I have drawn the 8 cubes and I have drawn the 1 1 1 plane on that. Now I need to arrange such that they have a common vertex and corresponding to their origin of the axis. and I need to show that they form an octahedron. So now let's try to answer it. Now arrange this in the such a way that it will form an octahedron. Any guesses? So let's say this is my 8 cubes. Let's say this is my 1 1 1 1 1 1 1 1 1 1 plane. Okay. Now second I will draw something like this. Like this. And this, I'll draw some dotted line here so that you know these two are overlapping each other. Okay. This is my two plane. Similarly, at the bottom also I'll get the plane here. This is also 1 plane. And here also I'll get something like this at the bottom. So it will follow this 1 plane. Okay. Similarly, if I draw here, let me change the color here. This is 1 plane. Okay. And here also, if I draw, let's say this is for the second case. So here you can see you are getting an octahedron. So by this way, we have proved this question that they have the 8 cubes and they have the common vertex, and we have drawn the 1 family of the plane. So this way we have answered the last question of our today's session. So till now, if any doubts are there, then please ask, or otherwise we will end our session here itself. So I'm just scrolling through the questions. If any doubt in the questions, just you can ask. You can stop me there and you can ask. So I think no doubts are there. So we will end our session here itself, and we'll meet in the next session. So thank you everyone for attending. So I am ending the meeting now.